Good afternoon. So today we have the pleasure to welcome Leonid Polterovich from Tel Aviv University. And he will give a very interdisciplinary talk from Fokker Planck to contact geometry and thermodynamics.
Let me thank the organizers for the kind invitation. It's a great pleasure to be here. So this is a joint work with Mikhail Entov and Leonid Polterovich. And the motto of the talk is as follows, that geometry, and namely contact geometry of the thermodynamic phase space, I will explain all the words, and PDEs, specifically the Fokker-Planck equation, which can be viewed as a heat equation with the Witten-Laplacian functions, coexist when they describe different stages of non-equilibrium thermodynamic processes. And while our contribution, and actually our contribution will be a little bit kind of in the spirit of this incident with the dog, so when the dog did not bark, so when this Fokker-Planck equation does not play the role, so geometry plays kind of major role, and that's what will be observed, yeah. But anyway, I will discuss both subjects. So let me start with the model. So the state space is in principle manifold with a volume form, but finite number of points is good for me, and it will be like this in the main example. And we'll look at probability densities on this space, okay? So Hamiltonian depends on the point of the state space and extra variable. So extra variable is intensive or control parameter in thermodynamics, and without this extra variable there is no story. So simply kind of all the contact geometry kind of happens, I mean, on the cotangent bundle to the space of these parameters times extra variable, right? So these are absolutely key, and in the example which we'll consider, so we'll consider some kind of magnet, yeah, with the magnetic external magnetic field which we can change. So this magnetic field will be this control parameter. So entropy is a function of no, absolutely not. Yeah, it's and actually I mean about a finite number of points. I'm totally serious. Zero structure. So the only thing I need measure, and you can happily kind of think that measure of each point is 1. Okay, and this is already deep example. Yeah, because all the symplectic geometry, as I said, will be, I mean, this notation Q is not arbitrary. Like Q then will be P. So entropy is minus integral rho ln rho d mu. Well, I will use this definition. So in rare cases in this story, but not in the one I'm kind of presenting today, one wants to have positive entropy, so then one adds some kind of additive constant, I mean, to make everybody happy. So free energy is very important object. So this is a function on which depends on this external parameter and density, and this is like this. So this is minus beta inverse S of R. So beta inverse is actually temperature, right? Plus integral over m h q of m rho of m d mu of m. So average of the Hamiltonian. And in order to find equilibrium, one should solve variational problems. So find rho so that this free energy goes to minimum. Q is fixed, so for each Q we have kind of its own variational problem. And this is well-known kind of story in equilibrium thermodynamics. So there is solution, which is Gibbs distribution. Rho equals to e in the power minus beta h divided by the partition function. And this partition function is just integral e in the power beta h d mu over m.
You integrate also the real variable in the...
Pardon me? Yes, it's integration over, think about sum, kind of. Yeah, so over the finite number of points. Okay, so now this is, in a sense, kind of quite a dramatic moment in equilibrium thermodynamics, because we found for given temperature and for given value of parameter q, equilibrium distribution. So at the end of the day, the kind of our points of the state space will be distributed in this way. Okay. So one also looks at generalized pressures, so extensive variables, so which are derivatives of this minus d phi dq. So phi is this free energy, so it's average of dh dqi rho d mu. So sometimes, I mean, this theory with q's is called response theory, yeah, or linear response theory when h depends on q linearly. So we're trying to understand how the system reacts to the change of the parameters. So that's kind of the main physical concern. Okay. So for one parameter, again, geometers kind of are not on the stage. Okay. So now it is convenient to bookkeep global thermodynamic parameters in the so-called thermodynamic phase space. And this idea goes back to Gibbs or Critiadori. So it's n plus 1 dimensional space, which bookkeeps the following things. So P are these kind of pressures, right? So generalized pressures, so reactions to the change of parameters, parameters themselves, and the free energy with sign minus. So 2n plus 1 dimensional space. And note that Gibbs distribution depends on Q. So in the equilibrium, this free energy equals to Z equals to minus phi of Q rho G of Q. So this is Gibbs measure. But now if we differentiate it with respect to U, we notice that rho is critical point of phi. And so this derivative is kind of d phi d rho 0, so we get that dz minus pdq equals to 0. And this is a so-called fundamental thermodynamic relation. And we view it like this. So we say that equilibrium submanifold lambda, which consists of all equilibrium z of q, p of q, is tangent to the kernel of this one form. This is one form on the thermodynamic phase space, yeah, which is called the Gibbs form. And such submanifolds are called Legendrian submanifolds. So it has kind of dimension q, so dimension n in this story, and it is tangent to the kernels of this form. Okay, so glossary is that lambda is contact form, its kernel contact structure, and lambda is Legendrian submanifold. So I mean, this is picture from Wikipedia. So this is the standard complex contact structure in R3, dz minus pdq. And you see that this space of kernels, so it's space of two planes, somehow kind of rotates, yeah? So it's extremely non-integrable thing. So this means that if you want to produce a two-dimensional object tangent to this thing, you will fail. So the maximal possible submanifold which is tangent to such a structure is one-dimensional on this picture, and this is exactly Legendrian submanifold. So this is our situations. And somehow these contact structures are subject of the science which is called symplectic topology. Okay, so this is just a cousin of symplectic structure on a manifold in various ways. And one can in principle say quite a lot. But I believe that this picture, including kind of importance of this contact form, was known to Gibbs. So far I did not say kind of anything new at all. Okay, so we will discuss the following example. So this is Curie-Weiss magnet. So in kind of sometimes it is called mean field Ising model. So we take complete graph with n vertices, and state configuration space are functions on the graph to minus 1, 1. So you can think like this. So this is your graph, and on each vertex, so there is vector up or vector down. So these are your spins. So mean spin is just sum of ones and minus ones over the graph. And it takes values in this set -1, -1 plus 2 over n, and so on. Okay? And Hamiltonian is minus n qm plus bm square over 2. And this is understood like this, that bm square over 2 is like energy of interaction, b is positive parameter, and q is an external magnetic field. So you have this kind of combination of spins. It's also kind of a little magnet, yeah? And you put it into near the source of magnetic field, also in this direction, up, down. And so then reactions look like this. So if the Q is very large, so then it's quite likely that all the spins will be up. And if Q is very small, it's very likely that all spins will look down. Okay? So now there is a remarkable thing that this Hamiltonian H depends only on M. And hence, instead of looking at this huge kind of configuration space, right? So you have functions on the complete graph to minus 1, 1, so it's like 2 in the power n points. We can reduce it to this remarkable space, which consists of, roughly speaking, like n points, yeah? And n plus 1 points. And one can make a reduction from this space of 2 in the power n spin configuration to a much smaller space of cardinality n plus 1. But how one makes a reduction? So you have to recalculate entropy in particular, right? And when you recalculate entropy, you get certain terms, and you basically get that the new Hamiltonian, which depends on m, looks like this. So it's capital N times some function plus kind of small terms. And this function, for instance, if you have that b times beta is bigger than 1, so it looks like this. So it has 2 local minima, 1 local maxima, and this structure will be of certain importance for further discussion. Okay, so kind of it's interesting when it has several critical points. And pressure per particle kind of, so in this situation is just magnetization. So it's integral m rho d mu, okay? So somehow now it's clear what are our parameters: magnetic field, magnetization, so kind of average spin of our magnet, and free energy per particle. Okay. So what we do, so we take this equilibrium Legendrian for lambda n, and objective is the following: we want to describe thermodynamic limit when n goes to plus infinity of the rescaled equilibrium Legendrian of the Curie-Weiss model. So it's given by specific formula. So z equals to minus f, where f is given this function, and df dp equals to 0. And you see this Legendrian. I mean, I don't want to draw pictures in dimension 3. I will show you 2 projections. So one projection is to PQ plane, and another projection is to ZQ plane. So you see, projection is quite non-trivial kind. Yes, you have some cusps and so on. So now we want to understand the following thing. So this is kind of limiting object, right? But let's describe the limit. And a thermodynamic limit looks like this. So in red, you see here pictures for finite n, maybe very large. And then n goes to infinity, and what you basically get, you get this green part, okay? And of course, I mean this part, this vertical segment. So somehow in thermodynamic limit, actually, you will get non-smooth picture. So your Legendrian will consist of 2 pieces and vertical segment joining them. Okay, in dimension 3. Wait a second. That's of course a good question. Yeah. So now, I mean, this green thing is called stable part. And blue, I mean, that's the puzzle, right? So blue is metastable, and black is called unstable. And they, I mean, to make a correct statement, so you will pass to 3-dimensional space. We have 2 smooth branches and this vertical segment, so we can analytically extend these branches, so we will get the full thing. So one can say that blue thing is obtained and the black thing is obtained by analytic continuation of this picture, okay, in dimension 3 and projection. And so this is a absolutely mysterious kind of story, right? So you just do some senseless from physical viewpoint procedure, right? So you have kind of, I mean, you develop the story, you started with equilibrium Legendrians, you pass to thermodynamic limit, you see some piecewise smooth stuff, right? So the smooth branch is actually analytic, admit analytic continuation. So the question is, what is this? Okay, and so then the point is the following, that in equilibrium thermodynamics you cannot see them, but in non-equilibrium you can. Okay, so now we will pass to a discussion of non-equilibrium thermodynamics, and I will return to this kind of metastable branches. So relaxation to equilibrium. So here comes kind of some connection to this program actually. So it goes kind of principle of relaxation is to minimize the free energy. Okay, so we are kind of taking as a law of nature, kind of is related to second law of thermodynamics, that free energy kind of decreases along thermodynamic processes, and we will just go to minimum. Yeah, so we want to minimize this thing. Well, we want to minimize this thing over all rows, kind of, yeah. So what does it mean? So we'll solve gradient equation d rho dt equals to minus gradient phi. Okay. But here comes the following question. Well, I wrote this gradient, yeah, but this gradient should be on the space of densities. And so which kind of measure, which kind of metric we consider on the space of densities? And the answer is that we consider gradient with respect to variable rho with respect to Wasserstein Riemannian metric on this space of densities, and this was developed by Otto and Lott. I think Otto observed that gradient flow of with respect to Wasserstein of free energy is Fokker-Planck, which is of course kind of remarkable thing because Fokker-Planck equation was known kind of in probably in the first half of 20th century, and Wasserstein I've seen by my own eyes. So what is Wasserstein Riemannian metric? So look. Let's do the following thing. So here indeed kind of some PDs enter the play. And they enter the play in an unpleasant way, okay? Unpleasant way meaning that there are some boundary conditions, okay? And there is some also non very nice behavior of Hamiltonian near the boundary. So I will completely ignore this at the moment. So I'm doing kind of wild assumption that my manifold M is a closed manifold. So in Curie-Weiss model, it will be interval minus 1, 1. It will be kind of limiting space for this kind of potential values of spins, and then we have to accurately say what happens at the boundary points. Okay. So but for closed manifold, you do the following procedure. So you identify a rho dot with unique function psi on M with zero mean, so that rho dot equals to minus divergence rho gradient psi. Okay? And so then you just set rho 1 dot times rho 2 dot W to be integral over M, gradient psi 1, gradient psi 2, rho d mu. So this is this Wasserstein Riemannian metric. Okay? So yeah, so you can ask me the following question actually, so at this point. Very good, but what does it mean kind of to fix a Riemannian metric on M? I mean, I'm trying to describe physical model, okay, and we believe that, system, independently of human mind, the Riemannian geometry somehow is going to Gibbs distribution. And this is very mysterious point. So I don't know the answer. So I think that for each metric there is its own model, and in Curie-Weiss we have pretty kind of indirect kind of way of arguing how to choose this metric, and I will mention it. Okay, so I would say this is first thing which I kind of don't completely understand in this story, but there are several. But yeah, fixing the metric is troubling. Anyway, after all this, you really get Fokker-Planck equation, which is d rho dt equals to 1 over beta n Laplacian rho plus divergence rho gradient f. Okay, and n is large, so you can say that you have small parameter at the Laplacian. And its appearance is interesting in the sense that, as I mentioned, this Fokker-Planck noticed that this term is kind of responsible for diffusion, and this term is responsible for drift across the along the gradient vector field. Was used by physicists to analyze relaxation in thermodynamics. Somehow, I mean, this model works. Okay, so yeah. So we in our childhood were okay. So yeah, we're taught that yeah, something is powerful because it is correct. So yeah, so it's exactly the story. Yeah. So
Usually, Fokker-Planck is a function applies to functions of position and velocity. Fokker-Planck applies to functions in position and velocity.
No. I think it's Poisson-Vlasov or something like this, position and velocity. Yeah. So this is on configuration. Yeah, but it's also kind of, you see, it's densities on the state space. Yeah. So it depends which kind of state space. Okay. So now, interestingly enough, this Fokker-Planck equation is conjugate to certain fancy operator, which is called Witten-Laplacian on functions. And so Fokker-Planck operator is this, I will denote it H Laplacian plus divergence rho gradient. H is beta n in the power minus 1. And Witten-Laplacian is the following thing. So it's operator D star with some indices times D with some indices on functions. And this D star F over 2H is deformation of the differential. So it goes like this. So it's H e in the power F over 2H D E in F over 2HU, and D star is adjoint to this operator. Okay? And so we deform differential with functions. So this when we write kind of our Witten-Laplacian in this form, so then we see that I mean it's positive operator. Obviously, it has kind of discrete spectrum. Okay, and there was a really long story how this and Gibbs density corresponds to ground state. Okay, so that's kind of for sure. And so then there was a story how eigenvalues and eigenfunctions behave when f, for instance, is a Morse function. And that's very exciting story because this ground state is concentrated near the absolute minimum, but there is a spectral gap. So spectral gap will be important for our understanding. So it can be read from the, at least asymptotically, from the Morse portrait, from the barcode. And log of first eigenvalue is minus c divided by h, and c is the length of the longest bar and finest bar in the barcode of this function. So description goes back to Arrhenius, so Eyring, Kramers, Friedland, Wenzel, Witten, Hilfer, Nier, Schostrand, and at the end, recently, Lepetryuk and Viterbo. I think these three guys related it to modern Morse theory. So here is what I mean. So assume that this is my function f, 2 minima, 1 maxima. This is absolute minimum. So here is concentrated the spectral here is concentrated the ground state. And spectral gap is controlled, so I said kind of something about finite bars. So these finite bars, roughly speaking, measure kind of oscillation of functions. And here, this is obviously kind of difference between saddle and second minimum, okay? Or I mean, depending in which dimension you view this picture, kind of. Dimension one, it's local maximum, local maximum, local minimum. So this is the bar of interest, and it controls everything. And somehow you see, huh? Yes. So this is not a bar. So I mean, what are these bars? So you are trying to cut kind of this picture, yeah, and view how topology changes, kind of. Yeah. Yes, it's first of all kind of changes here. You're saying, okay, we'll discuss this later. Yes, so of course, I mean, it changes. So it was like this. So you see, I mean, this thing disappeared, and now I'm with minimum, which goes to the infinity. Done. We'll handle this, okay? So, right. So, yeah, actually, I mean, this in principle impossible because endpoints of the bars corresponds to points of different indices. Should the difference of Morse indices to be one, okay? Okay, and this another way. So that's the picture. So remember, I mean, that this first kind of eigenvalue, yeah, so is extremely. I mean, this spectral gap is extremely small. It's extremely small, and so now this brings us to the next part of the discussion, which is discussion of metastability. So okay, I will do this on a little bit kind of popular level. So metastable thermodynamic states are characterized by the following properties. So first of all, if a system starts in this state, so it's likely to take a long time to go out, and when it's gotten out, so it's unlikely to return. Okay, so somehow it's a fake equilibrium. Yeah, so you have this evolution in the space of measures. So your system kind of spends huge amount of time near some fake equilibrium and then goes to the actual equilibrium. So this is a textbook example of metastability. So it's called super cold water. Yeah, so you can do it at home. You put a bottle of water in the fridge. So quite often when you take out the water, it's still liquid. So then you shake it, it becomes kind of, it becomes ice, as it should be, right? So another kind of, so this means that being kind of overcooled, but liquid is some kind of equilibrium, but unstable equilibrium. So well, at home I usually do the following. I do kind of dual experiment, which is called overheated water. You make a cup of tea in the microwave, yeah, and you just wait. Yeah, so then I mean, if you overdo it, it blow up. Yeah, and so no, it's safe. So simply everything will be kind of filled with water. Okay, this I did actually. Okay. Yeah. Okay. So anyway, I mean, this is metastability, and then in '63, Glauber suggested a remarkable model, which actually kind of it's a simple, rather simple-minded, I would say, model of how the thermodynamic system should return to equilibrium, right? So it's a Markov chain, it converges to stable equilibrium, it's ergodic, and indeed it exhibits, I mean, this was understood much later, amazing phenomenon, I mean, this metastability, so somehow it should be understood like this, that I mean, system sits in metastable state along and then goes kind of to the stable state, or if you wish, I mean, you know, it's diffusion equation, so it oscillates kind of near metastable state. At some point, there will be a large deviation, a large oscillation, which will enable it to cross here, and then it, boom, kind of return to stable state. Okay. So somehow this was on probabilistic level understood. So limiting dynamics. So in limiting dynamics is just ODE. Yeah. So this diffusion term is lost, and ODE is strange because kind of it shows slightly different behavior, right? So it actually has two stable. So metastable became stable, and unstable remains unstable. So somehow looking at this idea, we understand how drift behaves, roughly speaking, but not how, I mean, the system behaves. So and this kind of, as you see, I mean, these points correspond to this strange kind of blue and black and green parts of the Legendre. Okay. So the conjecture is that Fokker-Planck reproduces Markov chain metastability. We were unable to prove this. Maybe we will at some point, but yeah, so I don't know. So what we kind of can do, so for finite n, state space is a lattice with the mesh 2 over n. So you remember this picture. And then, interestingly, that this thermodynamic limit, in order to kind of do things, it becomes also a limit of metric spaces. So somehow this grid converges to the segment. And in the limit, all the action happens to the segment. So now potential strategy to understand metastability here is to compare to an auxiliary system of minus 1, 1. So we keep coefficient 1 over n at diffusion. We have no coefficient at the drift, but however, we already passed to the continuous model. So it's kind of partial kind of passage to limit. And what is the promise? The promise is that you remember, I mean, we have this exponentially small spectral gap. And spectral gap is exactly kind of responsible for the speed of converging to equilibrium if you start near metastable thing, right? So it will go very, very slowly. Yeah. So diffusion. So then you can do the following thing. So and this we worked out. So you can take this Glauber equation as kind of absolute truth. So then you can find Riemannian metric, very specific Riemannian metric, for which kind of Glauber dynamics in some sense corresponds to at least drift in Fokker-Planck dynamics. Okay, and then you really prove that drift term is equivalent up to some transformation to Glauber OD after, I mean, change of variables. And okay, but now you have to do this carefully, and you have on the segment minus 1, 1 a bunch of problems. So first of all, you need boundary conditions. So it's Robin boundary condition, which corresponds to the fact that probability flux through the boundary is 0. Kind of your point cannot move segment. Probability cannot move. Your magnetization kind of cannot move segment minus 1, 1. Okay, and moreover, the derivative of f has logarithmic singularity at plus minus 1. So somehow this kind of complete analysis here was not accomplished. So we kind of don't know how actually kind of Fokker-Planck behaves here, and open problem is to compare this with, I mean, Fokker-Planck dynamics with Glauber dynamics. Okay. Yeah, and by the way, I mean, because we are on the segment in a manifold with boundary, right? So then we have to use Neumann boundary condition in the definition of Wasserstein metric. So I pretended it was a closed manifold. It's not the case. So you see that there is kind of the whole bunch of difficulties from the viewpoint of PDEs here. Okay, so now I'm coming to the kind of main point of the talk. So something which I think something kind of from our perspective interesting happens. So it's a jump of temperature and field. So system is the same, Curie-wise magnet and spins, you have positive interaction, and assume that temperature jumps from T0 to T1, and magnetic fields also jumps from Q to Q plus A. So the model which I like to kind of consider is the following, that we have this kind of kit for Curie-wise, so magnet with magnetic field, and move it from one room to another room. In another room, temperature is higher, and there is also external source of magnetic field. Okay. And so then happens the following thing. So we were in the initial state, so in some Gibbs distribution rho 0 n corresponding to parameters b beta 0 q. So then final state we will relax towards rho 1 of n, so another Gibbs distribution with parameters b beta 1 q plus a. And we can write formulas for free energies with kind of corresponding to this change of parameters, and we will view this jump q goes to q plus a geometrically. Namely, I mean, equilibrium Legendrian for the terminal system is obtained from the one with parameter q by shift by a along the q axis. So kind of we added external field, we just shifted our Legendrian. Okay. So somehow this is a really good, I mean, initial and terminal system has good description. And what we will do, you remember that in this thermodynamic phase space, there are coordinates z, p, and q. Sometimes it's useful to forget z, to project everything to pq plane. So then kind of the resulting submanifold is called Lagrangian, so namely the form dp dq, and it vanishes. Okay. Very good. So now back to the story. So let me restate it. So there is a relaxation which I did kind of defining in two steps. So first, instantaneous jump. So density and Q and magnetization remain constant, but free energy changes. Okay, so free energy gives us kind of new possibilities. And so then on the second step 2 happens relaxation, namely gradient flow equation activated with F1 as kind of potential, right? So, and I mean, we're going along its gradient. And rho 0 of n as initial condition, so it's kind of wrong Gibbs distribution, which is not Gibbs distribution of F1, goes with the gradient of F1 towards Gibbs distribution of F1. Okay, so very simple model. But then there is the phenomenon. So we're kind of more or less arriving to a dramatic moment in the talk. Yeah, so it's highlight. So we claim that for fixed parameters T0, Ta, and A, there exists special value of the external magnetic field, so that in the thermodynamic limit happens the following, that actually both Gibbs distributions coincide. And why this could happen? Because we have a so-called large deviation principle in this model. So when in thermodynamic limit, Gibbs distributions kind of becomes closer and closer to the delta measure, okay? And in principle, I mean, this delta measure is concentrated at a point, and we can actually write down that kind of these measures are actually at F0 prime Q star and F1 prime Q star, right? So when these Legendrians, which we project, are given kind of by equations p equals to F1 prime Q and p equals F0 prime Q. So Fi of Q is nothing else but free energy in the equilibrium. Okay. And so this points exactly corresponds to intersection of these two Lagrangians. And if you wish, kind of in the level of contact topology, it corresponds to a vertical segment between two Legendrian when we leave these Lagrangians in the space with extra coordinate. Okay, and so then happens the following: that second step of our system in the limit is void. I mean, we're already in the equilibrium. Yeah, so I mean, there is no slow relaxation. So everything kind of is finished. Yeah, so we jumped and we are done. Okay, so now this special value Q star corresponds to intersection point of two Lagrangians, or it's called the rep chord. I will explain shortly what is this, joining these two Legendrian submanifold. And interpretation which I just gave is that these rep chords correspond to ultra-fast processes. So they are ultra-fast because kind of slow evolution to equilibrium with Fokker-Planck equation is absent. Okay? And so it's kind of, I mean, I explained to you how it works, roughly speaking, in Fokker-Planck, so we can discuss more general situations where this kind of discussion is rigorous. Okay? Any questions? Yes, rho is distribution in yes, and so that's exactly kind of we say that look, p this equation equals to this equation. So my m is p. So two values of p for certain q star coincide. So that's exactly what is written here. Okay. So now let me say a word about contact geometry. So I will use slightly more general settings. So we have a manifold, and contact manifold is T star X with canonical coordinates PQ times R of Z with the contact form dz minus PDQ. So it's called first jet space. Okay. And rep vector field in this situation is the following. So it's just vertical vector field. Okay. So it is defined by some relations that lambda v equals to 1 and IVD lambda equals to 0, but this you should not kind of worry about. So now rep chords in this contact, with respect to this contact form, are pieces of trajectories which are just parallel to the z-axis, so just vertical pieces. And one of the central problem of contact topology is to find rep chords joining to Legendrian submanifolds. And the reason is the following. So why it's kind of possible, yeah, I mean, to develop some theory. Because if you have very simple Legendrian, so let's say first is just zero section, as z equals to p equals to 0. And lambda 1 is graph of first jet of a function. So z equals to f of q, p equals to d of dq. Okay? So then this chords corresponds to critical points of f. So d of dq equals to 0. So right, p equals to 0. So now this of course happens when your Legendrian submanifold is graphical. So then there exists a function and you can basically do this thing, and so then you do your Morse theory kind of story, and you get chords which is in amounts corresponding to kind of total Bethe number of a manifold. So it's kind of pretty nice thing. But now one of the motivating questions in symplectic topology was like this. So assume we start deform these Legendrians in the class of Legendrians so that they lose graphicality. So then this argument already doesn't hold. And so then there exist non-trivial methods of contact topology which still enable us to detect, I mean, this and that amount of chords. Okay, so of course, I mean, this thermodynamic model which I am considering, again, kind of is troubling because people prefer closed manifolds, and we work kind of on R and so, okay, so which is a kind of difficulty. And the deep result is that the chords persist under Legendrian deformations, not necessarily graphical. It's Chaperon, Chikhanov, it's 1990s, yeah. But for instance, if you slightly perturb this form, I'm not sure whether it has a physical meaning. So then the problem becomes kind of even more difficult and even more modern method I need to do this. Okay, so here is a little application to Curie. So consider that indeed we have a jump as before. So T0 jumped to T1 and magnetic field jumped by Y, and lambda 0 and lambda 1 are initial and terminal Legendrian submanifolds respectively. And so then assume that I perturbed by some reason kind of, in this situation we just calculated everything. But now we applied some perturbation to lambda 1. So lambda 1 was deformed among Legendrians, not necessarily graphical, okay, so that it does not hit lambda 0. So the claim is that there is still a rep chord starting at lambda 0 and ending at G1 lambda 1. So this is rigorous result. And this corresponds, proof goes through contact topology, and interpretation is that G1 is perturbation of the terminal equilibrium, and the kind of physical nature of perturbations is interesting question which we are discussing now. So kind of the rules of the game here are that you are always kind of, you want to start with macroscopic model. Yeah, I mean, we are not gods, so we cannot kind of do things in space of macroscopic parameters, and then so then you want to kind of change something in the macroscopic model and see what you view here, right? And well, and that's I mean, not it's kind of not so trivial, okay? But I think we will kind of do something, at least in some models. So here is a conclusion, yeah. So of this part, so that ultra-fast instantaneous processes, so we assume kind of concentration of Gibbs measure, it's large deviation principle, so it corresponds to rep chords connecting equilibrium Legendrian submanifolds in the thermodynamic limit, right? So this is the new finding of our work with Entov and Rizhik. And here is an open problem, which I think is kind of nice to address this open problem in the PD community. So take such a chord, show that for finite n, so you see, I mean, we found this chord in thermodynamic limit, right? So, and interpreted it there, but in life, n is huge but finite, okay? And so we want to show that for finite n, the genuine Fokker-Planck evolution of thermodynamic variables z and p lies in the small neighborhood of this chord. So somehow we want to show that actually, I mean, this chord, which is obtained by, okay, so to say, a little bit scholastic process, so passing to thermodynamic limit and then kind of finding the chord and so on. So actually, it corresponds to genuine solution of Fokker-Planck equation for finite n. So extra kind of, I don't know, difficulty or not difficulty, but for finite n, you know, your space is finite set of points, so your Fokker-Planck will be a kind of difference equation. Yeah, and so there is science about this, so it's extremely unpleasant. Yes, that's exactly, I would say that you can view it as discretization of the limit, or vice versa. You can view limit as the limit of discrete systems. Okay, but now here is the point from which I don't know yet the exit kind of, that there is also coefficient at diffusion 1 over n. So when n goes to infinity, formally speaking, this thing disappears. But we know that it is not. So this means that one should play with kind of different terms in different scales, and we cannot do it correctly. Yeah. So that's the point. Stefan, you are looking through. Yeah.
And the Fokker-Planck equation acts on functions of the continuous space.
Yes, but you can write difference equation. So actually, it's not us. Huh?
You wrote the equation.
Yes, so there will be difference Laplacian. So the guy called, I think, Maas, if I'm pronouncing correctly, has science about this, and this kind of our first paper with Entov and Rizhik, we worked this out. Okay, but our main result was that we developed kind of drift. I think that the fact that discrete drift corresponds to limiting drift, we did absolutely correctly. Okay, but we are unable to compare evolutions and things like this. Okay. And so now I wonder, and this is pretty much, I mean, this discrete equation is pretty much kind of complicated. A Ginian, I mean this discrete. Yeah, I mean discrete. Okay, how in terms of time, what's going on? 10 minutes, okay. So then let me, tell you a story. So which kind of, I had this summer a very nice conversation with Nikit Nekrasov, who, when I asked him whether our results resemble him something, so he said me, sure, kind of go to imaginary time. I mean, to imaginary temperature. Okay, and so then you will, and so it turns out, yeah, yeah. Okay, probably he said correctly, yeah, but I mean, I have some picture in mind, so I will stick to it. So, so in this or another way, kind of, there is certain quantum analogy between thermodynamics and quantum mechanics, okay? And so, namely, if you consider kind of, you know, that, so first, that kind of, when you write this expression e in the power minus I beta h, right? And so if instead of beta you will write I divided by h bar t, you will get kind of quantum evolution, okay? And let me kind of say a couple of words about this. I'm very shy. Okay. No, now I'm entering some waters, kind of, I hardly understand. Well, except some formal manipulations. I mean, it's a little bit romantic. So what I think remarkable, so let's discuss it. So first of all, consider the following picture. So we do quantum mechanics, we consider two Lagrangian submanifolds in T star x, so graphical, so xi equals to differential of function fj. And to this Lagrangian, we consider the state which amplitude is a of x h bar, not so important to us, but what is important that the phase is e in the power I divided by h bar f of x. And then one has the following formula that for if our Lagrangians have a finite number of transversal intersections, so then you can express via some kind of complicated formula scalar product of these two functions. Of course, I mean when h bar kind asymptotically with respect to h bar, and remarkably, this scalar product goes along the points where differentials of f1 equals to differential of f2. Okay, so this is kind of exactly, I mean, this condition, I want to say. Yeah, so you see here you have two functions f0 and f1, and we are looking at the points where derivatives are the same. So it's kind of exactly the same points, okay? So physical meaning of, I will not read you this formula, it's not so important. Important that the sum is over this point. So physical meaning is the following, that if we normalize this thing so that norm of u1 and u2 equals to 1, so the absolute value square of this thing is transition, what is called transition probability from u1 to u2. So if your kind of observable is projection to u2, so you want to measure u2, right? So if you apply it to u1, the probability that you will get still u1 is kind of exactly this thing. Okay, so so one can say that Lagrangian intersection points are communication channels between quantum states. So that's what we learn, kind of, what we learn from this picture. So now weak rotation, so this is this change of time. So Schrödinger evolution operator is e in the power minus I divided by h bar th hat, so quantum Hamiltonian. set t to be minus h bar beta, where beta is a real number. So then this quantum evolution becomes e in the power minus beta h bar. And taking trace, we see the quantum partition function, that trace e in the power minus beta h bar equals to trace u at point minus h bar beta. So this is absolutely kind of nice partition function. So free energy is defined as in classical case 1 over beta ln z of beta, and we use that trace is quantum analog of the integral. Okay. Well, or you can view like this, that if you define density of states of your Hamiltonian, so this trace u of minus IH bar beta is Fourier transform of density of states, and the partition function is Laplace transform. So there is some duality between two things. Okay, and so then we go back to our thermodynamic Legendrian, so we consider Lagrangian projections, as I said, so we forget the Z, and we compare with kind of, we're doing WKB quantization. So we write the same things, Uj with, which is Hj in the power I over H bar Fj, with H bar equals to beta n inverse. So even kind of the number of particles enters into this thing. So exponent matches thermodynamic scaling. And we get that ultra-fast processes, which corresponds to intersection points, so they are thermodynamic communication channels. Okay, so there is certain duality between these two pictures. Okay, so and which means that if we would do Wick rotation from the very beginning, so maybe we could have guessed the original result, but we of course did not do it. Okay, so that's probably kind of what I wanted to say.
Okay, so any questions, the audience?
So, any interpretations of prior?
I think that, no, I don't know about interpretations, but there is kind of funny thing that, I mean, there is part of the spectrum which is exponentially small, which corresponds to critical points of f function. And then you have, I mean, the rest is, I believe, of order 1 or something like this. So there is a huge, so there is kind of one part of the spectrum and another part of the spectrum. And that's what was observed by Witten, right? And so then people kind of rushed into this.
But the exponentially small is not just one eigenvalue.
Yeah.
There can be several metastable states with different exponentially small eigenvalues.
Yes, they correspond to critical points. So all Morse kind of, I mean, all Morse portrait of the function in sense is encoded in this part of the spectrum.
Point of index de local minima, that shows up.
I think it's complicated. Not all.
Yes, you know what? I think you are right actually, because Witten. Okay, sorry. So on functions one should look at critical points of index 0 and bars which correspond to critical points of index 0. So then I can go to forms and so on. Okay, and so then points index of points will correspond to degree of, yes. So that's, yeah. Thank you. You corrected me. Yeah. Okay. Yeah.
I think there's a precise understanding also of the corresponding eigenstates. The way they are concentrated near the.
Yes. Yeah, but I think that quite fortunately, I think. Yes, I did not make a mistake, because I mean this is also kind of index 0. Yeah, and yeah. So on this picture kind of, yeah. So indices are correct.
But here you only investigated the situation when the two this super fast process or ultra fast process, when by accident the two solutions, the two magnetizations are the same.
Yes.
But, can you describe also time evolution, when you do the jump, when you jump, that is when you apply the change of parameters suddenly. What happens to the how this magnetization changes?
Yeah, I mean, I certainly cannot. So that's the right question to ask. So, and we tried. So it's probably, I believe, from what we discussed, it should be done like this: that you write also down Fokker Planck, but you speed up the parameter kind of. Yeah. So, for instance, I don't know. So you just consider continuous parameter. Yeah. So which depends on time, but this time, let's say, is very short and the jump is large, and then you try to analyze this. No, this we did not do. Yeah.
But somehow I did not understand how this contact geometry interpretation allows you to analyze the thermodynamics. Is it just a geometric feature or that?
No, I think that actually kind of, so let's see. Okay, so let me, that's maybe kind of, right. So I want to consider the following thing. So there is the notion of optical trap. Okay, so it's a similar model. So you have a laser beam, right? So which you kind of and it allows you to manipulate tiny particles like cells and bits in a liquid. And near the center of the trap, the particle experiences a restoring force, which is basically harmonic oscillator. So then, moreover, what you can do, and this is absolutely remarkable. I mean, if you have an actual spring, I cannot imagine an experiment which allows you to change kind of the stiffness of the spring. But here you simply change intensity of the laser, and you kind of, and you change, I mean, this spring parameter. So then in this model, you can do absolutely the same, kind of what I described. Yeah, so you have a jump of stiffness and external field, you get a ultra fast process. So this is kind of absolutely, I mean, you can do this absolutely rigorously. Okay, so now, okay, I mean, probably I should switch off recording. Okay, but now kind of a dream, okay, a dream. These things can be done in laboratory, okay? So now we can do the following. So we can arrange an experiment. So I kind of challenge experimental physicists to arrange an experiment, which will observe the following thing, that I don't know kind of about speed of the process, but what you can certainly measure, you can measure work of certain kind of cycle. Yeah, so that's I learned from Bernard Derrida kind of. So you, for given value of parameters, you make a cycle, yeah. So you jump, you go to equilibrium, you jump back, you go to equilibrium, you calculate the work, okay? And then, I mean, at some point, I think at summer, I started to panic because, I mean, I thought that the work kind of invented after many efforts a perpetuum mobile, yeah, which is not a very good kind of situation. But Derrida calculated that actually the work is positive. And then kind of if you calculate carefully, you see that for these values of parameter per particle, work is capital O1 over n, and for other values of parameter, it's O1. And so this means that in principle, one can try to do this kind of cycle suggested by Derrida in laboratory and check. And if this is true, so then, I mean, that's the success of quantum geometry in thermodynamics.
No more question? Sorry, thank you, Leonid.